We are now starting lesson C8, Introduction to Sequences. We will probably be working on this for a couple of days. Here are the standards that are listed, and this is the lesson in your book. Now, as you read through these different I can statements, the thing I want you to be aware of is I'm not going to read them to you because they're there for you and you can look back at them, and so that we have plenty of time for the video. As you look at this video, there's going to be a lot that's new, and you may want to re-watch it a couple of times. So when we talk about a sequence is simply an ordered list of numbers that often form a pattern. Each number is called a term of our sequence. So here's some examples: 2, 4, 6, 8, 10. Can you tell what's happening each time? It looks like we are adding the same number, right? 3, 6, 12, 24, 48. In this one, if we are looking at it, again, here it looks like we're adding 2. Here it looks like we're always multiplying by 2. So we have different kind of sequences. And then this last one is a really special one. It's actually called the Fibonacci sequence. 0, 1, and then you add the first two terms to get the next one. So there's many different sequences that you're going to see, but they form a pattern. As we are looking at these patterns, and as we look at these, as you look at problem 1, generating terms in a sequence, it says look at the rectangular numbers. And as we look at these rectangular numbers, first you see 2, then you see a 2 by 3, which is 6, then you see a 3 by 4, which is 12, and here you see a 4 by 5, which is 20. And so if we are looking at this, it says what are the first 6 terms in our sequence? So the first rectangular number is 2, then we have 6, then we have 12, then we have 20. And if we are looking at our dots, we might be kind of thinking as we look at this, oh, the first number had 2, then we had 6, then we had 12, then we had, change this to 20. And I only listed the first 4, and we need to keep going. Well, if we look at the pattern, here the pattern was, in our rectangular number, 1 times 2, length times width. Next we went 2 times 3, that gave us 6. Here we have 3 times 4, that gives us 12. Here we have 4 times 5, that gives us 20. So we're starting to see a pattern, and we might think, oh, I bet the next one is 5 times 6, and it is 30 in our pattern. And then we are going to be looking at 6 times 7, which gives us the 42. And so we've listed the first 6 numbers in our sequence. So if we are looking at these, what's the pattern? So the pattern was to find the area of the rectangle. What did we do? We took 1 times 2. Next we took 2 times 3. We took 3 times 4. So we continued with 5 times 6. So it keeps, as we look at that, it says we start, if we look at our table, start with 2. And each time we add 4, then we're adding 6, then we're adding 8. So adding, first time we add 4, then we add 6, then we add 8, then we add 10, then we add 12, and we're going to keep that pattern going as we look at it. So if we continue adding here we added 10, here we're going to add 11. You could do the 7 times 8, or you could say, okay, we're going to keep adding, so 56, we'd get 72 and 90. It says, is the set of ordered pairs a function? So 1, 2, if we are looking at these, this is like our x and our y. Is it a function if we think of this as an ordered pair? For each input, is there one output? And our answer to that should be yes, it's a function. Why is it a function? Each input has one output. Each input has one output. If we're looking at our domain, well, think about this. If we're looking at rectangular numbers, can we have anything negative? No. Can we have fractions or decimals? No. So what is our domain? Our domain is going to be our counting numbers. So it can't even have 0 as a side. Counting numbers. Starting at 0, 1, 2, actually starting at 1, 2, 3. How many dots would be needed to make the 10th figure? So again, we could continue our pattern, noticing that each time we were adding, here we added on 18. So to get our next one, we're going to have to add on 20. 90 plus 20 gives us 110 dots. That's one way to look at it. It says, can we write an expression for our pattern? This is a different type of notation you're going to see. We're going to talk about a to the n. So when we look at this, instead of our function notation that we looked at before, we are now going to have a to the n, and it's talking about a sequence. And what was happening is that if we take a look at this, we have the n term times the next term in the sequence. So if we were thinking about this as our n, this is n, and this is n plus 1. If it's 9, how did we get this answer? We took 9 times, and if we are thinking about that, 9 times n plus 1 would be our 9 times 10. So what is our pattern for this model? It is a to the n, looking at that term, or usually we're going to write it as just our n term, and it's times n plus 1. So if we wanted to find the 100th rectangular number, we want to use this pattern. It's saying, what is a to the 100? And that is going to be equal to 100 times 100 plus 1, which is 100 times 101. What is 100 times 101? A to the 100th number, the 100th rectangular number, is going to be 10,100 when you multiply that on your calculator. Now again, I know this is hard stuff. We're going to probably have this broken into 2 videos because it is hard to explain too. Watch it a couple of times as we go through it. So we now, as we look at problem 2, want to write a sequence for, this time we want to look at the first 4 triangular numbers. So if you think of a triangular number, if I have 1 dot, the number of dots in the figure is going to be 1. That's our first triangular number. Next, if I'm doing a triangular number, my second one has 3 dots in it. Next, triangular number, again as I do that, I'm going to have 3 dots across the bottom. I'm just adding a row each time to the one previously. So I'm now up to 6. And if I was going to draw the first 4 triangular numbers, now I need 4 on the bottom, 3 going up, 2 and 1. So if I had 6 here, I added on 4 to get 10. So if I'm looking for a pattern, what's happening as I look at this? I am adding first 2, then I added 3, then I added 4. So we can easily fill in our table at this point. Okay, so if we were filling in our table, we're going to keep going with that pattern. I'm going to add 5 and get 15, add 6, 21, add 7, get 28, add 8, 36, and continue and adding and get 45. So each time I'm adding. But I also want you to think of what is the formula for area of a. So if we think of what area of a triangle is, base times height times a half. In this case, if we looking at our numbers to get 1, we're going to take 1 times 2 and dividing it by 2, that's our 1/2. That comes out to give us 1, this number. If we take area of the next triangle and we take 2 times 3, taking 2 times the next number down in our table, 3, and divide it by 2, we get 3. So we're always looking for patterns. We saw the pattern where we were adding. Now we want to look for a pattern of how did we get these numbers? How did we get 6? Oh, 3 times 4 divided by 2. 12 divided by 2 is 6. Let's see if it continues. If we go down here, 6 times 7 divided by 2. 42 divided by 2 is 21. Does it continue with 45? Oh, with 9. We are looking at 9 times 10, and then we're dividing by 2, which gives us 45. So as we are looking, it's always tough, and these problems are a little harder ones. The first 9 triangular numbers, what is the formula for the nth one? thinking about this area formula. So we are going to say to get our nth term, a to the n is equal to the number n that we are looking at, always times the next one. Well, if it's the next number down, that is n plus 1, and we're dividing that whole thing by 2. Again, this is hard stuff, so go back and replay it if you need to. We're going to go to the next page, that next set of notes on the bottom. Here is where you're going to see the different notation. So it says we use special notation to show sequences. The notation has lots of subscripts. The 10th triangular number is 55. This is how we write it. T to the 10 equals 55. T sub 10 equals 55, which is the 10th number in the term, the 10th term in our sequence, and it is 55. It says the little number 10 is called the subscript or the index, and it indicates the position of the term. So this one would be telling us the 4th term in the sequence is 10. The 3rd term in the sequence is 6. So as you look at those, how are sequences different than functions? So sequence and a function, their domains are natural numbers usually. We can represent them using function notation or sequence notation. We are really going to concentrate on sequence notation now. So we've been working with function notation. We are now going to concentrate on sequence notation. So as you look at the problems, this is what we will be really concentrating on. So the first thing that we want to take a look at is what's called an illicit formula. We will probably today do this video, and I might start the next one and have a little more of the second half of the notes. But an explicit formula is one that describes any term in a sequence by its position. The formula can be written for triangular numbers. The explicit formula would be used to calculate the nth term, or explicitly by substituting in n. So if I wanted to find the 20th term, t to the n equals n times n plus 1, the next number in the sequence, times 2. So as we look at that, I name the sequence t because we're talking about triangular numbers, and I could use any other number if I wanted to. What's the 20th term? Well, if I want to look at that, I'm going to write my formula, n times n plus 1, all divided by 2. What is our n, our t value here? Well, we were trying to find the 20th term. So we're going to have 20 times 21 divided by 2. You're asking, how did I get 21? Because it says n plus 1. So if n is 20, the next one has to be 21. We're going to be multiplying those two and then dividing by 2, which gives us 210. You could divide this way first and get 10 times 21 to get 210. It says consider the squares or natural numbers. So complete the first table of squares. So think about your square numbers. 1, 4, 9, 16, 25, 36, 49. What if we want to find the 250th? Well, what is our pattern? What is the nth term? What did we do each time? We took 1 squared, 2 squared, 5 squared, 7 squared. So this is going to be 7 squared. This is going to be n squared. If we want to find t to the 250, we're going to go to our formula, n to the second. Only thing now, we're going to use 250 and square it on our calculator, which gives us 62,500. The next type of formula is recursive. I'm going to stop this video at this point. We will look at this one and the other one in class tomorrow. Like I said, we're going to spend a few days on this.